Section 311, related rates. Walking through example 5, expanding square. The sides of a square increases in length at a rate of 2 meters per second. So the first thing I did was I drew a picture. I drew a picture of a square. I labeled it S for sides. And then I gave my information was the rate of change of the sides. So ds dt in respect to time is 2 meters per second. And the first thing I want to do then is know that I'm going to use the formula for the area of a square to be s times s, or s squared. So for part A, it asks at what rate is the area of the square changing when the sides are 10 meters long? So for part A, I'm looking for the rate of change in the area and when the side is 10 meters. Now remember, I do not want to plug or substitute in 10 meters for S until after I take the derivative, because if I substitute too early, it freezes or holds the value in place. So because I want to know the rate of change as it's changing, I'm taking the area formula and taking the derivative with respect to t, and I have that the rate of change of the area is equal to 2s, and because it's with respect to t, an implicit differentiation, I have to multiply it by the ds dt chain rule. So from here, I can have all the information. I have S and I have ds dt to substitute in order to find the rate of change for the area. So when I go ahead and I substitute 2 meters for the length of the side of the square times the rate of change of 2 meters per second for how the side is changing, and then I'm going to go ahead and calculate this out, and I should have on this one, I substituted the wrong thing in, sorry. Let me check again. I have 2 times 10 meters is my side length, and my rate of change is 2 meters per second. There's where I wanted to substitute in. So from here, I'm going to multiply my coefficients, and though multiplying my units, I have meters squared per second. That's the rate of change of the area when the side length is 10 meters. So part B says, well, the same thing. Let's find what is the rate of change of the area, but when the side length is 20 meters. So I've already had the calculation from above for what is the rate of change of the area. And then I'm going to just substitute in my new information. The side length is 20 meters times the rate of change of 2 meters per second. And then I should get from here 80 meters squared per second is the rate of change for the area. Part C, though, said graph how the rate of change of the area varies with the side length. So it's asking you for a relationship. And since it's asking me to graph it, I'm basically going to graph on a Cartesian plane, and remember, all Cartesian planes is the relationship of some x with some y, or in our case, we're really, instead of saying y, I'm really going to say area, and we're going to talk about instead of x, sides. All right, so from here, what I really want to have is ordered pairs of what was the side and what was the rate of change of the area. So if this is the way I want to look at it, I've got from parts A and part B 2 points. The first one would have been, if I can get a point here, my first point would have been when side was 10 meters, my rate of change was 40 meters squared per second. Didn't have my M in here for meters, sorry. And then my second point would be 20 meters for the side. My rate of change was 80 meters squared per second. And then we can go ahead and graph these points. I should have 10, 40, and 20, 80. It looks like this should be how I could graph the relationship of the rate of change of the area varying with the side length. That makes sense because it's really the derivative graph. And if you go back to our derivative here, it's a linear equation, but with that chain rule of how the side is changing. So we've graphed that problem.